download from Triple J.
For more music, current affairs, comedy and culture, triplej.net.au.
And now...
It's 7 after 11 on a Thursday morning, which is the time that we always say good morning, Dr. Karl. And Karl, we're very excited this morning to have a very special guest in the studio from the UK, a physicist who is the Royal Society University Research Fellow based in particle physics, quite a mouthful, at the University of Manchester. He holds a chair in particle physics, works on the Atlas experiment at CERN in Geneva. He also is a well-known BBC presenter on television and on the radio, and he used to front a band called D-Ream, which featured their big hit. And things can only get better because Professor Brian Cox is with us on this Thursday morning. Hello, Brian.
Hiya. I should say I didn't front the band. I hid at the back.
Sorry, you didn't
playing
front.
Keyboards.
You were the keys
so,
player.
Yeah, out of the limelight.
But what a song. Now, you gave up being a musician to do a degree in particle physics. You got it the wrong way around, Brian.
Well, no, in some ways it was the reverse. I have been interested in physics and interested in astronomy, particularly from as far back as I can remember. But at the age of 15, I just became interested in not necessarily music, but just being a pop star, really. So it was kind of rather specific.
Yeah.
And so I sort of almost took a break. So I was just talking to a load of kids from some schools around in this area. And I said to them that the point is that if you want to be a pop star, that's fine, but it's better to do it after you've finished school.
Yeah.
And I was lucky because I finished my exams, I did it, and so when I was 18, I could essentially have a gap year, essentially as we call it in Britain, which is what I did. But it became a gap 4 years because we got a record deal. So it was kind of physicist always, part-time pop star for a bit, and then back to physics again.
You really were living the dream, literally living the dream.
There was once actually, do you know the band Take That? I suppose you do know the band.
Yes.
Well, D-Ream supported Take That, and I was in D-Ream at the time I was doing my undergraduate degree in Manchester, and there was one day when I finished lab, took my white coat off, walked up the road and went on stage supporting Take That, and then came back out and then went back to the physics lab again and carried on.
Wow.
So yeah, it was a dual life.
Well, now you're a superstar in the science world. A lot of people incredibly excited that you were going to be joining Dr. Karl today. You in particular, when I mentioned a few months ago, do you want to have Brian Cox in? Almost jumped out of your chair, Karl.
I was incredibly excited because, and I can summarise what you do in this way. I showed your book around to the people in Master Control down at ABC, this fine book called Wonders of the Solar System, and people saying things, I'll just summarise it. He shows us the interesting stuff without stupidifying it or dumbing it down. And I think that's a wonderful talent that you've got. And it's fantastic and big enough for you.
I mean, I find that, and you must find the same, when you talk to people, they want to understand. So if you talk about quantum theory, for example, then people want to understand. They don't want to be told, oh, it's a bit strange. And look, Schrodinger's cat, isn't that funny? People actually want to understand. And I think we are in great danger of underestimating people. That's the point.
Well, by the way, we've got people tuning into you from Spain.
Paris.
Who got up at 1 o'clock in the morning. They're all ready for you. But I should introduce you to our audience. I'll give you an example. We had, who was it? Who was the black hole guy? Kip Thorne,
yes.
Oh, yes.
and Roger Penrose on the show.
Yes.
Well,
and some guy rang in with a question about black holes, and he was going through the question and asking some specific details. And then Roger Penrose said, "Excuse me, sir, are you a postgraduate or you're doing a PhD?" And the guy said, "No, mate, I'm fucking Forky." I'll explain it.
Language warning.
I'll explain that to you. It's Australian for... No, sir. For my daily employment, I drive a forklift truck to earn bread for my family.
Right.
So this was this forky guy who asked this deep question. So that's the sort of audience that we've got.
Yeah. Okay. And it's
A curious audience who are wanting to give us a call and ask you both questions. 1300 0555 36 is the number. If you can't get through but you've got a comment, we can take comments or answers on text and Twitter, but we only take questions through the call because we want to hear your voice. But if you've got a comment, text us on 0439 75 7555, or you can tweet Dr. Karl direct, DoctorKarl. We're talking today with Brian Cox, Professor Brian Cox, and also Dr. Karl. And Brian, just to give the audience a bit of a heads up, what is your area of expertise other than, particle physics is obviously your main area, but what else do you know in the science world that you can answer questions on?
Well, I'll have a go at almost anything. Interestingly, actually, I just finished a BBC series which is going to be on here in the new year on ABC called Wonders of Life, which is really I suppose you could describe it as a physicist's look at biology. So I've just had a crash course over 2 years on evolutionary and molecular biology, which was fascinating because when I left biology as an academic subject back in the 80s, it was completely different. The rate of increase in knowledge in biology, the questions such as how did life begin? Now we're beginning to get theories that are gaining a lot of ground, and I wouldn't say a consensus is appearing, but yeah, I think the progress is with DNA sequencing as well. Actually, it's quite remarkable the precision with which you can answer questions like how long ago was there a common ancestor between a chimpanzee and a lemur, let's say, or something. And the precision now that we can answer those questions because of DNA sequencing is incredible. So I can rabbit on. I'm very excited about biology as well as astrophysics and particle physics and cosmology.
Take advantage of those brains. 2 scientists for the price of 1 this morning, which is, as always, free. 1300 0555 36 is the number to call. Let's head to Willoughby first, where Richard's been waiting on the line. Good morning, Richard.
Is a universe with nothing but time possible? A universe with no stars, no stuff, no space, just time. I've been...
No quantum vacuum?
I'm sorry?
Not even a quantum vacuum.
What's that?
It's actually exactly the right thing to say, Dr. Karl. Because there are 2 things. I mean, first of all, it might be worth describing the universe as we know it now, the general view, which is down to Einstein, which is we live in a 4-dimensional universe. So there's a thing called space-time, and it's inappropriate and wrong to try and separate the two. The mixture between space and time depends on a lot of things, how you move in relative to other people.
So you can't separate them?
No, I mean, a very good example there is the GPS satellite system. People think of these things as esoteric. I'm often asked questions like, what a waste of time trying to understand these things. But it turns out that if you look at the rate at which time passes on a satellite in orbit relative to the ground, then it's different. And the way in Einstein's theory that's described is that the mixture between space and time is changed by gravitational field and by the fact those satellites are moving relative to us. But the upshot of that is that the clocks on the GPS satellites drift by 38,000 nanoseconds per day relative to the clocks on the ground. And why did I say that? Well, light travels 1 foot in 1 nanosecond. So that translates into a 38,000 feet per day drift in the position as measured by the GPS system. So you have to correct for the fact that time moves at a different rate on the satellite than it does on the ground. So it's engineering. It's an engineering problem. And understanding how to do that leads to the satellite navigation system. So it's real engineering rather than physics, but it's based on the fact that space and time are mixed together. There's a very famous quote by Minkowski, one of Einstein's tutors actually, who said that from henceforth space and time as individual elements are destined to, I don't know, be left in the past, I think it was. He said it in a very poetic way.
But what about matter? Suppose there are 0 atoms. There are no quarks, no electrons.
Yeah.
Okay.
This is why your comment on the quantum vacuum is very important, because then you have a question about the laws of physics. So the quantum vacuum is essentially an expression of the laws, the forces of nature, the laws of physics. And there's no such thing as empty space. So you can't even divorce space from atoms and things because the quantum vacuum is fizzing with particles, electrons and anti-electrons and quarks and antiquarks fizzing in and out of existence, and this is as observable consequences. It's really and now we've discovered at CERN, I should say, that the vacuum is even far from being full of electrons and quarks. It's full of Higgs particles, jammed full of Higgs particles. I mean, if you naively calculate how much energy there is in the Higgs field in 1 cubic metre of empty space, it turns out there's more energy than the sun outputs in 1,000 years.
What?
Per cubic metre.
Say that again. In 1 cubic metre, I'm writing this down, in 1 cubic metre of supposedly empty space, that's equal to the energy output of the sun for
1,000 years.
Wow, okay.
And it's something, I can't remember what it is in joules. It's something like 10 to the 30-something joules. I can't remember.
Okay.
But
let me work for Richard again. So if we remove all the atoms from the universe, time still goes on. But what if we can remove, but because of the quantum vacuum? Suppose we can remove the quantum vacuum.
You'd have to remove the laws of physics as well, because once you've got laws of physics, quantum laws of physics, then the vacuum is far from empty. That's the point.
That's right.
And so really, what you're talking about with a universe just full of time is, first of all, you've got to answer questions about what space is and what, as you rightly said, what laws exist in that universe and what the quantum vacuum looks like, which essentially defines the universe. I mean, I was talking to somebody the other day about this, a cosmologist actually, and it's almost true to say that given the structure of the vacuum, by which you mean the laws of physics, and the structure of space-time, everything else pretty much follows. Right? There's pretty much, you don't have to do much from then on.
Except when you get into the complexity of human life and life itself, and whole different.
Well, but that you know, even that, I mean, it's an emergent property which emerges given the laws of physics. It is probably it's certainly the most the purest way of looking at life in a scientific sense.
Well, thank you for taking us down the rabbit hole, Richard and Willoughby. What a
Very
question
good
to start with. Thanks for the call, Richard.
Question, and will you be in Cairns on Tuesday?
For the total eclipse.
No, unfortunately not. I'll be in Perth, just about to go home actually. So I'll see a partial eclipse from Perth.
Yeah, I'll be up there at 6:39 in the morning.
I believe we have on the line Elise calling in from Ballarat. Hi, Elise.
G'day, doctors.
Good morning.
Hello, Dr. Elise.
How are you all today?
Good.
Very well.
Okay.
What's your question?
I have a question about Newton's unit of force and how that relates to the gravity we know on Earth as opposed to, say, the gravity from the Sun and the gravity from Jupiter or other stars and that kind of thing. I'm trying to wrap my head around, the concept of Newton's and gravity.
Yeah. Well, the answer is that actually Newton's theory is in some ways very difficult to understand. There's a better theory. The Newton's theory of gravity was replaced by Einstein's theory of general relativity in 1915, which is mathematically more difficult but conceptually easier. So the best description we have of gravity, due to Einstein, is that so we live in space and time. Space-time, as Einstein would have called it.
Yeah.
And mass, or indeed energy, anything that sits in the universe curves space and time.
Yeah.
And we move in straight lines through space and time. And that's it. That's his law of gravity. And so what if you look at the Earth and you say, what is it doing around the sun?
Yeah.
Well, it's in free fall. It's following a straight line through curved space. Okay. And that looks to us like an orbit. And the best explanation I think I could give of this is if you imagine standing on the equator with a friend of yours and just start walking upwards, start walking north, parallel. Well, a parallel line on the surface of the Earth is a line of longitude. So you'll bump into them at the pole. You'll meet them. So if you didn't know that you were walking on a curved surface, you'd say there was a force between you that was attracting you together because you're moving towards each other. But actually, it's a fiction in a way. What actually is happening is you're moving on a straight line on the curved surface of the Earth. And that's what Einstein says gravity is. So basically, everything is following and moving in straight lines through curved space. And if you look at that from the vantage point of someone who's sort of in the space and can't really see the curvature, then they look like curved lines. It looks like there's a force.
Is a way of saying that then that mass tells the fabric of space-time how to curve, and in response, that other matter then follows that curved space.
Exactly. So Einstein's equations actually just tell you how space and time curve, mass and energy actually. So both curve space and time. So it actually answered a beautiful question, which is why do all objects fall at the same rate in a gravitational field? Why does a tank fall at the same rate as a table tennis ball? Well, it does.
Would they fall faster towards the sun? They would, wouldn't they?
But they'd still.
The mass of the sun would mean that it has that greater force of gravity or the greater pulling power.
That's right.
So they would fall faster.
Exactly, but what that's saying is that the sun has curbed space and time more.
Okay.
But actually, the question as to why they fall at the same rate, even though obviously, in Newton's language, the force of gravity is stronger on a tank than a table tennis ball because the tank's more massive. However, in Einstein's picture, all that's happening is they're falling together. They're following straight lines together through the same curved space, and so they follow the same path. So they fall at the same rate. Newton had no explanation for that.
Hey, thanks for the call, Elise.
That's all right. Thank you very much.
Good on you, mate. Let's head now to Adelaide, where Heath's on the phone. Hey, Heath.
Yeah, g'day, how are you?
Very well. What's your question?
Not too long ago, I watched a TV show fictional or non-fictional, I'm not sure. But they go into a different theory about the purpose of the Great Pyramid of Giza. You've probably heard it before, but they reckon it was probably more likely built as an energy source. They said that if you were to pour a dilute hydrochloric solution down one of the chambers and hydrated zinc, I think it is, down the other chamber, it makes hydrogen in the bottom. It explodes and travels up through resonators into the King's chamber and then shoots an energy beam out the top. Have you heard that theory?
No.
I have.
Haven't.
I read crazy personal literature.
That sounds crazy. I mean, what is that? What is that theory? Does that theory make sense to you, Professor Brian Cox?
No. I don't know what. No, I think usually, actually, to make more sensible, usually there's a thing in science called Occam's razor, which really says that the simplest explanation is probably right, given nothing else. So there's what we find about grand ceremonial buildings, and I filmed at a few actually, is that they tend to be just that. They tend to be political statements. They tend to be things that are aggrandizing somebody. Some philanthropist built the things. And that, I mean, it seems to me to be a rather bizarre and inefficient power station. They'd have been better off inventing electricity, in my view. But there we are.
Which the Iraqis actually had electricity and had they had batteries, and we think that they used them 2,500 years ago for electroplating.
Yeah.
With regard to the pyramids, people keep on claiming that they're energy sources. Well, how come they've broken down? We do know that, according to the work by a certain Kate Spence from Cambridge, who's an Egyptologist, and relating to the precession of the Earth's orbit, that the North-South Pole sweeps out a circle every 20-something thousand years, that back in 2467 BC, when building pyramids was all the rage, the ones built at that time, they faced exactly north when they were lining up with the pole star, because that's where it was. The ones built earlier were off to one side. The ones built later were off to the other side. Small sample size, only 6, but nevertheless very suggestive.
You do find, actually, there's I've filmed at many places around the world where the astronomical alignments are very common. They're also very hard to prove, because it is also true that virtually every building you build is aligned with something, because there's a lot of interesting things in the sky. Yeah. But I think it is probably true to say that there were buildings in the ancient world that were aligned with things in the cosmos, because why wouldn't you do that?
So let me just get this straight. Are you going with the dominant paradigm put out by the imperialist fascist running dogs that run our society? Do you believe that the pyramids were or were not built as an energy source by aliens?
Well, he didn't say by aliens.
Oh, you left that
by
bit out.
Aliens. Then
normally
that would be,
aliens. They're
literally ridiculous.
Yeah.
Because I always think about this when people say that aliens built them. It's like, well, why is there no titanium, metal, anything? Why is it just made out of bits of sand?
Well, people have done...
Surely, wouldn't you find at least a spanner or something? Or wouldn't they have used... Why not use some steel? They'd come here in a flying saucer. Why would you then build something out
at
of
least
bits
a
of
gap filler or something?
So, yeah, anyway.
Thanks.
But we didn't say it to the benefit... Karl, I give him credit. He didn't say aliens.
It's true.
It was a statement about energy source, and that was a reasonable question in a sense. But the answer is that it's probably rather inefficient.
Hey, thanks for the call, Heath. We're going to have to leave it there, mate.
Sorry, Heath.
We've got a bunch of great comments coming through on the text line too. Thank you for everyone texting in on 0439 757 555. Jed in Canberra just had to hose out his car because his mind just exploded, he said. What a blown
How did he
minds.
coordinate himself to hose out his
Reflexes, man.
Only a scientist would follow that up with a question. Let's head to Port Macquarie where Chris is on the line. Good morning, Chris.
G'day, how you doing?
Great. What's your question?
My little question is more of a hypothetical. If matter and antimatter at the beginning of the universe had properly annihilated each other and formed a universe essentially of photons or of radiation, would the laws of physics as we know them today, equals mc square, or the second law of thermodynamics, for example, would they still exist? And if they would, what are they existing for?
So it's a very good question. The answer is yes, they would, because the laws of physics are independent of the things that happen, essentially. Well, we have to nuance that slightly. If you were listening earlier, we were talking about the quantum vacuum.
I did, yeah.
So you can't remove all electrons, let's say, from a universe. in the sense that the laws of quantum electrodynamics are there, and they allow for photons to produce electron and anti-electron pairs all the time. So you get this vacuum full of the things. But what you're referring to, though, is it's one of the great questions in particle physics, because given the laws of physics as they're stated at the moment, then you need a difference in behaviour between matter and antimatter in order to get anything in the universe. Because, as you rightly say, if everything's completely symmetric, then you make antimatter and antimatter in equal amounts, and then they annihilate each other again, and you get a universe full of photons. Yeah. So it's one of the great questions to search for a difference in behaviour between matter and antimatter. There is a difference. There is such a difference in the laws as we have them now, but it's not enough to describe the preponderance of matter over antimatter in the universe now. So it's an open question.
Can I just back up here a bit? So the universe started off and there was a slight preponderance of matter over antimatter by one part in a million.
They should get made in equal amounts. But they behave differently. So we do know there's a difference in behaviour, very slight, between matter and antimatter at the moment. So that can account for a difference in the ratios of them, because maybe, for example, it could just be that antimatter particles decay quicker than matter particles.
So what I used to think, but I'm wrong then, that there was a slight preponderance of matter over antimatter, and when they annihilated, what was left was the matter which led to us. Is that still...
So that could also be right, and that would suggest that the thing is that there is a difference in behaviour in the so-called standard model of particle physics, which has been observed. But it's not enough. So the precise mechanism, or the mechanism that led to the difference between matter and antimatter in the universe today is not known. People think it might be something to do with neutrinos. So there's a lot of work in looking at neutrino beams to try and see if there's any. So the technical term is CP violation, if anyone wants to look
parity.
it up. Yeah, but there isn't enough in the laws of physics now. So it's an open question.
Hey, Chris, we're going to have to leave it there. Sorry, mate. We've got heaps of callers waiting. Thanks for your call.
No worries, bye.
Cheryl is calling in from Taree this morning. Hi, Cheryl.
Hello.
Hello. What's your question?
This is my question. As physics can now confirm that there is so much about our world that cannot be perceived with our senses, even with special instruments, when will this picture of reality begin to supersede the largely material one, which still pervades our thinking about life?
Good question.
Well, the thing is that physics hasn't discovered anything that can't be perceived with our senses, because if it couldn't be perceived, then we wouldn't have discovered it. So what you might be referring to is the dark energy, for example, which is one of the great mysteries in modern theoretical physics, which is the energy that's responsible for driving the increasing rate of expansion of the universe. So an Australian Nobel Prize, actually, Brian Schmidt, 2 years ago, got a Nobel Prize for this, for showing that the universe is accelerating in its expansion. Now that causes an interesting problem, a fascinating problem for physics, because something has to do that. So you're talking about something, if you imagine the Big Bang and matter and energy being thrown out, then gravity is an attractive force. So everybody thought, well, the universe is undoubtedly going to be slowing down. And one of the questions 10 or 15, 20 years ago was, is there enough matter in it to stop it expanding and then recollapse it, the so-called Big Crunch? Now it turns out, by observation, that the universe is accelerating. So you have to look for something that can do that can drive that acceleration. Now, fascinatingly, earlier we talked about the Higgs particle. The Higgs particle, naively, if you look at something like the Higgs field, which we discovered this year, then it should do that job. And so you think, oh, that's wonderful. But when you do the calculation, you find that there's 10 to the power 120 times too much energy in the Higgs field to do that.
That'd be called a fairly major disconnect between theory and practice.
It's a very, very large error. The way that I often picture it is if you said, I'm going to count up to that number, and you started doing it with atoms. So imagine the atoms in front of you. Go 1 atom, 2, 3, 4. There are not enough atoms in the entire observable universe to count to that number. So it's a bit of a problem. But the point is, with reference to your question, so we have no evidence that there is anything in the universe. By definition, we have no evidence that there's anything that you can't observe, because if it was there, we couldn't observe it. So everything we know about that we've discovered has been observed by, it maybe indirectly by its effect on other things, but that's actually how we do observe things.
So we know that the dark energy, if you turned into matter, would account for 70-something% of the universe.
Yeah.
And we know it exists because the universe is expanding faster than it should be, but we don't know what it is.
It's accelerating.
It's accelerating.
So it's something, there are several theories. One is that it's a property of empty space. It's interesting, actually. Einstein had this in general relativity, Einstein's theory of gravity. You can have a term, you're allowed by the mathematics, which drives an acceleration.
The cosmological
expansion. That's
constant.
it, cosmological constant.
Okay, so the other bit that we can't see is dark matter, which accounts for 20-something% of the universe.
Yes.
And we know for sure, to answer Cheryl's question, we know for sure it's there by its gravitational effects. But what the heck it's made of, nobody knows.
Yeah, the common idea is that it must be some kind of subatomic particle that's not the kind that the world is made of. However, it's just, you can say, no, actually what it is we need to modify our theory of gravity. So there are, that's a more fringe view, but it's not ruled out that what you could be seeing. What you're really looking at is the gravitational effect of things. And this goes back to the questioner's question, actually. The observation is that things are not moving in the way we would expect under gravity. So the more likely explanation is that's because there's more stuff around than we can see.
I think to answer Cheryl's question, there is definitely more stuff we're going to discover in the future. There's so much we don't know.
90% of the universe.
99%, 99.99.
No wonder you guys love your jobs. Thanks for the call, Cheryl.
Thank you.
Adrian's calling in from Noosa. Good morning, Adrian.
Hey, how are you?
Hello, good. What's your question?
All right. It's my understanding that solar flares are a danger to astronauts in space because of those higher energy electromagnetic radiation that's produced by them.
Mm-hmm.
That stems to me a question: can superconductors be used in space? Like, is it low enough temperature in that vacuum, or does the solar radiation heat things up?
Actually, interestingly, the space itself, if you go to the coldest place in the universe, then you're looking at the temperature of what's called the cosmic microwave background. So it's the temperature the universe has cooled down to after 13.75 billion years of expansion.
How cold?
That's 2.7 degrees above absolute zero. The Large Hadron Collider operates at 1.9 degrees above absolute zero. So it's colder in order for these superconductors, as you call us, these magnets to function. So we have to cool the Large Hadron Collider down colder than anywhere in the universe. Actually, one of the engineers said to me, if there were no intelligent civilizations anywhere else in the universe, then there would be nothing that cold, because the universe is hotter than that. So it's not even the solar radiation. It's actually, if you go to the coldest place you can find, it's still hotter.
How do you even
than
get
the
it
Large
that
Hadron
cold?
Collider. It takes a while. It takes about a month to cool it down.
Wow. So
So you do it with all sorts of... It's a fridge, basically. It works like a refrigerator. You use liquid nitrogen, and then ultimately something called superfluid liquid helium, which is a very strange substance. It's still liquid. It doesn't freeze. It's still liquid at that temperature, so you can use it as a refrigerant. But it has weird properties. It flows out. If you pour it into a cup, it flows out of the cup. So it's very, very, very difficult to build
has a mind of its
27
own.
kilometres of machine with that in it. But there we are.
Thanks for the call, Adrian.
Thank you, Adrian.
Let's head to Olympic Park where Samuel is on the line. Good morning, Samuel.
Hello.
Hello, what's your question?
The fundamental forces of the universe, gravity, weak, strong electric forces, stuff like that, is it fine-tuned?
Ooh. Can you just explain the background to the four forces? This is a beautiful thing.
So the four forces that we know in the universe, there's electromagnetism, the weak nuclear force, the strong nuclear force, and gravity.
And that's it. They're the four. Remember those.
However,
they're the four forces that run everything that we know about.
Yeah, although actually electromagnetism and the weak force
Are
are now
married,
unified together, which
electro-weak.
is where the Higgs comes in, actually, and all that stuff. But and the question now I've forgotten, very professionally.
The question was, are the parameters of the universe fine-tuned?
Yeah.
Fine-tuning.
So there's some interesting observations that have been made about this. One is that in order to make carbon in stars, there's no carbon in the universe at the Big Bang, so it gets made in stars in nuclear reactions. And there's something called it's a very interesting discovery. It was called the Hoyle resonance. So Fred Hoyle, very famous astronomer in the 50s, pointed out that given what we knew about nuclear physics at the time, you couldn't make carbon in stars. It either wouldn't be made or it would get burnt to oxygen very quickly. And it turns out that indeed there's a particular configuration of a carbon nucleus which depends on the strengths of the forces. It's called an excited state. which allows for the rapid production of carbon in certain types of stars, and then allows for that carbon not to be made into oxygen. So carbon can exist, and therefore life can exist in the universe. And there's a lot of work been done on how precisely you can change the strengths of the forces to remove that, so that there would be no carbon. And actually, there's a lot of work been done. Some people say 1 in 1,000. Some people say 1 in 1,000,000. It's a very difficult calculation to do. But it is true to say that if you change the strengths of the forces by a small amount, but what I mean by small is open for debate, then you wouldn't get carbon in the universe. That's one example.
And there's a whole bunch of numbers in the universe that if they were just a little bit different, the universe as we know it, and then life as we know, which is basically on planet Earth, wouldn't exist. And the question was, did God fine-tune it, or are there an infinite number of universes in which just one of them is where we are and we know to talk about it because we're here?
One of the modern views, which comes out of string theory, is that actually when you say the universe, you mean this infinite multitude of universes with different laws of physics, different strengths of forces. They all exist in what people call a landscape. And so we're in the one where, for example, carbon can exist, and therefore life can exist.
Now, can we just leave the audience with this one?
You've got to be careful, though, because that's speculative stuff.
But I want to leave the audience with these things that you mentioned. The 4 forces that explain practically everything are the electromagnetic force.
Yes.
Right, remember that, audience? The strong nuclear force.
Yeah, that sticks the quarks together inside protons.
The weak nuclear force.
Yeah, which is unfamiliar but is responsible for radioactive beta decay. If you remember.
And then finally, the gravity force.
Yes.
Okay. Do that as your homework.
I feel like people are just going to be listening to this podcast 10 times to understand what is going down. There's a lot of information this morning and we're loving it. Thanks so much for the call, Samuel. You're with Zan on Triple J Mornings, and joining us, Dr. Karl, as he does every Thursday, and also special guest from Manchester, Professor Brian Cox, who's here doing a couple of sold-out talks tonight in Sydney and tomorrow in Melbourne, and also on the cusp of releasing a new book, Wonders of Life, which is also a BBC series, which will air in Australia. That's coming up early 2013. You've also got another series of stargazing starting.
Yeah.
And you have another book, which I'm sort of looking over there, and you can probably see the title closer than I can, which you released last year.
No, this one.
Yeah.
Quantum Universe. Everything that can happen does happen.
That's a good title for a book. Brian Cox is with us and answering your science questions. Try and squeeze a couple more in if you're lucky. 1300 0555 36. Let's head now to Dan, who's on the line from Leichhardt. Hi, Dan.
Hi there, how are you?
Very well. What's your question?
Hi, Brian, how are you?
Hello. Good, thanks, Dan.
Yeah, from Manchester too, mate. If you look at the stars, we're looking back in time. I appreciate that. And if you look at the distant stars, then we're looking further back in time. And, I've read and heard that if you look far enough away, then you're looking at traces of the Big Bang. What I can't get my head around is this, it's a geometry problem, really. How has that radiation from the Big Bang ended up on the Earth? Why isn't it why is it not at the edges of the universe?
It's a great question. I mean, the radiation you're referring to is called the cosmic microwave background. So the picture is the answer to your question is the Big Bang didn't occur at some place distant, far away from us. It occurred everywhere. So it occurred in your room as well as the space that you're sat in now, in your head. It occurred. So space has been expanding ever since. So you asked the question, what's the most distant thing you can see? Well, the universe was opaque before 380,000 years after the Big Bang because it was so dense and so hot that light didn't travel through it. So what you're seeing is the moment at which the universe became transparent, which is 380,000 years after the Big Bang. It's when electrons went into orbit around atoms, around nuclei, because it was cool enough for that to happen. And that light has been travelling ever since through the universe. So we can see it.
What's the geometry of that? Where is it? I still don't understand why it's not close to the edge of space-time as we know it now.
It's everywhere. It's everywhere. So that radiation is everywhere. So all of space-time, indeed, was at the Big Bang, and it's been stretching. So the ultimate messing with your head statement about that is if the universe is infinite now, which it may well be, we can't see beyond 13.7 billion years or so, but if it's infinite now, then it was always infinite and it was born infinite. So in other words, it's not like you had this big box which the universe expanded into. Space and time began at the Big Bang, according to our best theory, and it's been stretching ever since. So you're getting it's a very good thing to be confused about, but it's an odd geometry.
The one thing to walk away with is that the Big Bang happened in your belly button
Yes.
and on Andromeda and M81 and everywhere in the universe is where the Big Bang happened at the same time.
Hey, thanks for the call, Dan.
No worries. Thank you very much.
We've got Ella on the line from Fremantle. She's 9 years old. Good morning, Ella. Hello.
Good morning, Dr. Ella. How are you?
Hi, I'm just wondering how long does it take for the planets to align?
Well, the closest that they got was back in the 5th of May 2005 when the date was ever so conveniently 050505, and some people were saying that all of the planets, Mercury, Venus, Earth, all the way out to Pluto, I like Pluto being a planet, all the planets were in a dead straight line, and this would mean the end of the universe or the end of Earth as we know it. They were telling a little porky pie, a little white lie. In fact, the planets were not in a straight line, but spread out over 90 degrees of sky. So if a circle's got 360 degrees, they were 1/4 of a circle. And even if they were lined up exactly, the gravitational force on you would be less than the gravitational force of a fully loaded jumbo flying at 30,000 feet over your head.
Yeah. Carl Sagan, one of my heroes, used to say about this, because people think of things like astrology and think, well, there must be something, and He used to say the gravitational pull of the midwife is greater than the gravitational pull of Jupiter on a newly born baby.
Wow.
And that's true. So these things have no effect anyway. As Dr. Karl rightly said, when you say a line, you don't really mean a line. These things are spinning around in distant orbits at slightly different angles, and they don't really align.
One day they might get within 10 degrees of each other, or, but it's not going to be a big deal if it does.
Thanks so much for the call, Ella.
Thank you, Ella.
Bye.
Bye. Bye, Ella.
And I think that's about all the time we have this morning. Thanks so much for all your calls. I know that the phones were pretty rammed for the last hour, but we appreciate you trying. And for those who got through, appreciate your questions and all your texts that have been coming through, 0439 757 555. Don't forget, if you missed any of today or you just want to listen to it again and try and figure out if it makes more sense the second time around,
Look,
Some Big Theories, the podcast is available and will be up in a couple of hours, triplej.net.au.
And in fact, when I listen to podcasts, sometimes I have to pull over, stop the car, sit at the side of the road and play the same bit over, sometimes 5 or 6 times to fully understand it. This one, I think, is going to lead a very stuttering car journey for many people.
It's because of the excellence of the questions. That's why.
That's right, even if they're a forky.
Questions. Yes.
Professor Brian Cox, it's been such a pleasure having you in. We could probably talk to you for the rest of the day, but we have to let you go. You're going to hopefully be back in Australia, though, sometime soon.
Very soon, yeah. I want to bring my radio show, The Infinite Monkey Cage, here, which we do. I really want to do that. And Dr. Karl, you must be on if we do that, without a doubt.
I'm available too, guys.
Oh,
I'm
of
available
course.
too.
You can run it.
Thanks so much for joining us today, and enjoy the rest of your time here in Australia. Don't forget, Wonders of Life, the new BBC series with a book as well, is going to be out our way around February time. And Dr. Karl, we'll see you next week. Professor Brian Cox, thanks so much for joining us on Triple J.